Listen-only mode.
Good afternoon and welcome to today's webinar sponsored by the CTE Technical Assistance Center of New York. A few points before we begin. All attendees are initially muted. We will take comments and questions throughout the webinar. To pose a question, click the raise your hand icon and you will be announced and unmuted. You may also submit a question to be addressed by typing it into the questions pane on the control panel. All questions are logged and any unanswered questions can be addressed by today's presenter via email. If you become disconnected and cannot reconnect independently, please call us at 518-723-2137. Today's webinar is being recorded and will be available for viewing on the CTE Technical Assistance Center website at nyctecenter.org within 72 hours. If you have questions or suggestions regarding upcoming webinars, please contact us at ctetac@spnet.us.
Okay, welcome everyone. My name is Rich Scroy and I'm pleased to be offering the second in the Real World Real Math webinar series, the Algebra of Finance. This week we'll be looking at automobile algebra, that is algebra that is inherent in studies of the auto. On April 2nd and April 23rd, my colleague and co-author Rob Gerber will be doing two more in the same theme of the algebra of finance, and I hope you can join him then as well. I'd like to reiterate, if you were with me last week, there may be a couple of slides that will seem like they overlap, and of course they do, because they're very important, and this is one of them. The National Research Center for Career and Technical Education has a wonderful website that I encourage you to look at, and they talk about how they believe in a fully philosophy of contextualized curriculum integration. And I think that's the key to what we're going to be doing today. And that's also the key with the Common Core standards, because they talk a lot about mathematical modeling and putting math in context. So at the end of the talk, when this webinar is available, you might want to download it, and there'll be a number of things you might want to go back and refer to because it'll be just too much to copy down right now. What I do encourage you to do is have pencil and paper, because there will be times when we'll stop and you'll do a few things so that you can keep up with the mathematics that's going on. So today we're starting to look at automobile algebra, the algebra of the automobile, and there is so much inherent in this context. And what I found, I've been teaching this topic for many, many years, and especially juniors and seniors who are so excited about their first auto experience and buying a car and getting out to drive a car. They are very happy to see things like this talked about in a math classroom. I do have to do a little bit of a disclaimer here. Everything in this presentation is used with permission from Cengage Learning. Cengage Learning are the publishers of Rob and my book, Financial Algebra, and that's enough to be said about that right now. If you're interested, that's Cengage Learning. All right, I like to begin classes with a quote. I find that quotes offer an anchor to students, and I can use quotes as pre-instructional or post-instructional, and oftentimes I use them both ways. So let's take a look at some of these quotes. Some of them are mathematical, some of them are whimsical. You can define them any way you want and see if you might want to use them if you're doing this type of unit. The car has become an article of dress without which we feel uncertain, unclad, and incomplete. Marshall McLuhan. Never lend your car to anyone to whom you have given birth. Irma Bombeck. I like that one. I didn't take her advice with my own 3 daughters. If the automobile had followed the same development cycle as the computer, a Rolls Royce would today cost $100 and get 1,000,000 miles per gallon. I think that's an important one to look at if you're doing this in the context of mathematical studies. Why is it that the way the computer developed and the way a very ritzy car like the Rolls Royce developed are two different things? And that's a great discussion to have with kids. And then finally, it takes 8,460 bolts to assemble an automobile and 1 nut to scatter them all over the road. Let's begin. So what I like to do at the beginning of this unit is to introduce students to things that I think will grab their attention. And one of the things that grabs students' attention are gas prices. They're so young, they're used to gas prices in the $2 and $3 range. But what I like them to do is get a historical reference about gas prices so that they can get a better feel for what has happened over the course of many, many years. So let's take a look right now at this gas price chart that I have. It goes from 1950 to 2010 in increments of 5 years. And way back when, in 1950, the average price per gallon in this country was 27 cents. Now, I'm sure there are some places that you could have found it for less in the middle of the country, but this was the average price per gallon. Interestingly enough, there's a little bit of a blurb at the bottom here because students like some historical facts. In 1953, the Corvette had a base price of $3,498, which was very, very pricey for them. And there were only 300 of the cars manufactured, and you had nothing to worry about in terms of what color to choose because it only came in white. It would cost $5 to fill up the 18-gallon tank. And in 1960, think about this, the median annual income of a U.S. family was $5,600. So for gas to be 31 cents a gallon, that was pretty pricey at that time. Anyway, it's always fascinating to look at these numbers. So we now know what the average gas price was for last year in 2013. And what we're going to do with this chart now is to see if we can determine if past gas prices can predict future gas prices. And during all this, as the prices of gas have been going up and up and up, I noticed on the internet this great visual. I thought it was quite cute that it actually was taken somewhere where the prices were going higher and higher, and you pay an arm and a leg, and don't we all know it? So what we're going to look at right now is something that is a predictive mathematical tool known as linear regression. And those of you who were in my talk last week, we use linear regression to do some things with the stock market. And today we're going to use linear regression, which is taking a look at trends. We're going to use linear regression to examine if gas prices can predict future prices, gas prices. But first of all, I need to do a little bit of groundwork. And again, I apologize to those who were with me last week, but this will be fast. So first of all, if you have a single column of data, it is known as univariate data. In other words, if I was to go around my classroom and ask all the kids to count how much change they have in their pocket and record it, and then I make a list, that's a single list of data. It's a univariate data list. But if I have two pieces of data, pairs of numbers that are analyzed together, those are known as bivariate data. And we do something with that. We take those pairs of numbers and we graph them on a graph, something like you see here. And we graph the x, the first component, or the y, the second component, and we have a point. But the thing that we don't do is we do not connect these points because they're separate pieces of data. An interesting experiment you might want to do with kids is you measure their hand span when their hand is stretched out from thumb tip to pinky tip, and you measure their foot length. And now each kid has their own piece of bivariate data. And what we can do is we can analyze to see if there's any relationship between a person's hand span and a person's foot length. But what are we going to do with this? Well, let's go back and take a look and see if we have any correlation or association in those bivariate data. Some terminology. A positive correlation exists if the value of one variable increases when the value of the other increases. So notice, as the horizontal variable gets bigger, the vertical variable gets bigger, and that's why we have an upward trend here, and that's known as a positive correlation. A negative correlation exists if the value of one variable decreases when the value of the other variable increases. So notice, this horizontal variable is increasing, but look what's happening to the vertical variable. As the horizontal increases, the vertical decreases, and we have a negative correlation. So what we're going to want to look at now is to see if we can come up with some formula that would best fit the dots you see or the scatters that you see on those graphs. So let's now go back and take a look at the original chart I gave you. And instead of putting in the years, 1950, we're not going to do that. Instead of putting in the years, what I'm going to do is call it year 1 was 1950, year 2, 1955, etc., all the way down to year 13, which is 2010. And I added this in, it's $2.78 in 2010. Now, what we're going to do is we're going to have a graphing utility like the spreadsheet do the analysis for us. You could do all of this by hand, but it would take forever. You can use a graphing calculator, but I know many classrooms don't have graphing calculators. But most schools have access to computers where students can at least watch you do this in front of them and maybe take it home and do it on their own. So first we put the data in column A and column B, the year and the average price per gallon of the gasoline. Okay? Once we have that done, what we're going to do next is we are going to take a look at making a scatter plot. So what we do is we click on this charts, scatter, and marked scatter. And this is what we get. We get a graph that looks somewhat positive in its nature here. But we're really not sure what kind of trend it shows other than it looks like it's going up. But hey, it leveled off here, it leveled off here. So what you do is you click on any point in this chart in your Excel program, and they're going to be highlighted. And when you highlight these, we will now go and look for a line that fits those points the best way possible. That line is known as a trend line. We're looking for a trend. We're looking for a line that might be able to establish a trend for us and be a predictive line for us. Okay, so we hit on chart, and we go down and click on add a trend line. Now, there's lots of trend lines. As a matter of fact, the word line is a little deceiving because some of those trends could be trend curves. But for our purposes right now, what we're going to do is do linear, which is a trend line. So I come over here under options and I click linear. Then I go to options and I want the graph of this trend line displayed for us, so I'm going to click display equation on the chart. And again, look, I don't expect you to internalize this so quickly today. Download the program, take a look at it again, and you can write yourself some notes on how to do this in Excel if you're not familiar. Voila! There was the scatter plot, and superimposed over the scatter plot is now the equation of a line that will be predictive in nature because it shows some trending. And as a matter of fact, there's the graph of that line. It is a linear equation because x is raised to the first power. But you might say, but hey, look, that didn't connect the points. That looks pretty sloppy. There are more points that aren't even touching the line. But truth be told here, the way that this works is, this is the line that for most of the points, if you look at the vertical distance between the points in the line, it minimizes that distance. Now, how good of a predictor is it? Well, I'm guessing it might have been good in the middle here, but it's not so good as we get past 2010. But, say, Libby, that's what we get when we have linear. But we don't have to stick with linear. We can move ahead now, and we can look at a polynomial. Polynomial is going to give us a curve. And we have a variety of polynomials to pick from. By choosing a polynomial with different degrees, we will get a different level of certainty for our trend. So what I'm going to do first of all is I'm going to click on polynomial and then change the order to 2. 2 means the highest exponent in the polynomial is the squared term, and this is known as a quadratic equation. Notice now how different this looks than from the line. As a matter of fact, let me pull them both up so you can take a peek at this. On the left was our linear predictive equation, and on the right is our quadratic predictive equation. Which one looks better to you? And I think you'd have to say, well, the quadratic looks better. But what if we went and kicked it up one more degree? How about a third order equation, which is known as a cubic? And there's the cubic equation on top that I get. It's looking even better. One more, how about a fourth order equation? Now look at the fourth order equation. It even shows the little bit of a bump in the middle that there was present in the scatter plot. So that's enough. I mean, I can keep going and going and going. As a matter of fact, Excel only goes to 6 degrees or 6th order, but I think you get the picture here. Now what I would like to do is take each of those equations, the quadratic, the cubic, and the quartic, and go back to my Excel spreadsheet. And I put that equation in the first list, the cell here for the quadratic, the first cell here for the cubic, the first cell here for the quartic. And I filled down, and I got the predictions based upon those equations. So for the year 2010, the actual average price was $2.78. If you use the quadratic, you would have predicted $2.64. If you use the cubic, you would have predicted $2.75. And if you used the quartic, $2.81. And who's to say what's better? Well, it's a toss-up here between cubic and quartic. But how do we predict the average price for 2013? Now, we got to be careful here, and this is something students need to recognize when interpreting charts. The years went up in increments of 5. So if I would have said that 2013 was year 14, I'd be mistaken, because year 14 is 2015, and we have no data on 2015. So we got to think, well, wait a minute, if it's going up in years of 5, then what I need to do is to get from 13 to 14, I have to divide that single increment divide it by 5. And what I'm going to find out is that for each year past 2010, I have to go up by 0.2. That's what 1 divided by 5 is. So the year 2013 is year 13.6. Here's what I'm going to do. I'm going to put 13.6 in for the year, and now calculate using the quadratic, calculate using the cubic, calculate using the quartic, and that's what I get. Okay? So the actual price for that year, by the way, was $3.51. So even the quadratic, cubic, and quartic weren't that great a predictor, and we might have had to go even higher into a 5th degree or a 6th degree equation. Right, so you can see how linear regression can help us make some predictions rather than haphazardly saying, oh, I think it's going to be, we have some math to back us up. If you're doing this unit on automobiles, what I suggest you do is get hold of some useful websites like this one, gasbuddy.com. Great website because it gives you the up-to-the-minute gas prices in your area and all across the country. So use real numbers. Don't make things up. Here's another one, Kelley Blue Book, www.kbb.com. Excellent, excellent website that gives you used car and new car prices, as well as Edmunds.com that does exactly the same. I rely on these 3 websites whenever I'm doing the automobile unit. They're really good and easy to use, and your students can use it too if they're doing presentations. So we're going to do some work. Megan knows a coworker who's selling a used Honda. The car has 60,000 miles on it, and it is in good condition. She decides to do some research and obtains information on cars that are of a similar make and model, year, and condition on sale in her area. And she makes a list. Notice, here's the mileage, 21,000, the price was 22,000. 30,000 miles, the price was 19,000, etc., etc., etc. We now have a set of bivariate data, and we are going to look to see if there is a correlation, if there is a trend, and then we're going to look to see if we can use this to help Megan figure out what the price should be on a car that a friend is trying to sell her that has 60,000 miles, and is the price that the friend is stating a good price. So how do we do this? I put in the information, the bivariate data that we know, and I follow the steps that I did before to get my scatter plot, click on the points, get the trend line, and there is my trend line. And the linear regression equation is that. And I can use that to predict, I can use that to analyze the past and predict the future. And that's what I'm going to do. So now we introduce a concept of how good of a predictor is this line. And that's called the correlation coefficient, R. In the olden days, when I was in school, you'd have to use this formula, which was known as the Pearson product moment correlation coefficient formula, and the name was just as long as the formula, and it would take forever to figure out. But now on graphing calculators and Excel spreadsheets, you can get it very quickly. It's a number between -1 and 1 inclusive that's used to judge how closely the line fits the data. Negative correlation coefficients show negative correlation, and positives show positive. If the number that you get is near 0, that means that there was really very, very little relationship or association between the two. So correlation coefficients with an absolute value greater than 0, in other words, -0.75 to -1, 0.75 to +1, they're called strong correlations. And likewise, if they're less than 0.3 and -0.3, in between those two, they're weak. And you can see on the little graphic I have here, between -1 and 1, closer to the -1s and 1s, you'll get a strong correlation. Closer to the center, you'll get a weak correlation. So in this particular case, how do we find the correlation coefficient? Well, once again, Excel comes through for us. There is a formula called Correl, and it's right there. Correl array 1 and array 2. And what we did was I used Correl in the spreadsheet here, and I found out that I get a correlation coefficient of -0.97, which there's a very strong correlation between mileage and price. Okay, so what do we do with that? Well, we want to help Megan out. We want to help her figure out what's going on here. So we're going to use her linear regression equation of y equals -0.1625x plus 24,722, and we're going to plug in the mileage of 60,000 miles for x. And that's what I did right here. And when I do that, my predictive equation says at a mileage rate of 60,000 miles, based upon the other data that we have, the car price should be close to 15,000 miles. So Megan should go back to her friend, show her the math, and say, look, this is an outlier. Your price is really higher than what the market can withstand. And that's how mathematics can be used to help us out in making some decisions about automobiles as well. All right, let me stop. Just anybody have a question?
There are no questions,
Okay.
Rich.
Okay. So, well, we've looked at purchasing automobiles. Now let's look about once you've purchased it, we know that our car appreciates or depreciates. But for most cars, they depreciate. And depreciation happens in 3 distinct ways. One is known as linearly. In other words, your car loses the same value every year until it's worth nothing. It will depreciate exponentially, which doesn't mean the same value every year, but means approximately the same percentage every year. And then there's something known as the bathtub curve, which we're going to look at in a second. I'm going to hold off talking about that. So let's go to linear. Now, let me make it perfectly clear. In the real world, nothing depreciates linearly. It doesn't. That's just the way it works. You don't find that things will depreciate the same amount every single year. But in our real world, the Internal Revenue Service, when you have to depreciate something for them on your taxes, they depreciate linearly. So that's why we look at it as if it was true, because when you're calculating depreciation for the IRS, you depreciate linearly. So here's an example of something that you purchased in year 0 for $30,000, and after year 12, it depreciated to nothing. So when the car is purchased at time t equals 0, this, where the line intersects the vertical axis, that is how much the car costs. All right, now let's move over here and take a look at after a given period of time, the car has no value. So the y, the height is 0, and if you do this, this is 3, 6, 9, 12 years. After 12 years, it has no value. And everything in between, the car was depreciating by a certain amount per year. That's the explanation of linear depreciation. So let's look at an example. Suppose you purchase a car for $27,000, and according to your online research, this make and model of car loses all of its marketable value after 12 years. That is, it depreciates to a value of $0 12 years after the purchase date. If this car depreciates in a straight line form, what are the intercepts of the depreciation equation? Well, I showed that to you in the graph before, but now let's talk it through to make sure you understand it because it's a very important concept. X is going to represent the time in years. So the minimum value for X is 0 years. That's the year you purchased the car. Because the car totally depreciates after 12 years, there's nothing to be said of this car after 12 years. So the maximum value of X will be 12. Now let's look at the vertical axis. Well, the minimum value of the car is 0. It's worth nothing. And the maximum value of the car, unless it's a vintage or a classic car that's appreciated over time, it's going to be worth what you bought the car for, or $27,000. So here's a picture. Notice, in year 0, I paid $27,000 for that car. There's an intercept, there's a point. After 12 years, my car is worth nothing. There's the other point. And all you need are 2 points to determine a line. That's what the depreciation equation looks like for this particular model of car. All right, a car sells for D dollars and totally depreciates after T years. If this car straight line depreciates, what are the intercepts of the straight line depreciation equation? In other words, think about what we just did with numbers and now algebraize that situation. And the reason that we do this is because I want kids to ultimately be able to create their own formulas for the spreadsheets. So we take a situation that's numerical and now we symbolize it and algebraize it. So in this particular case here, the car's lifetime goes from 0 to T years. I mean, frankly, people drive cars that have no value. I have one of those. As a matter of fact, it has 300,000 miles on it. It's got no monetary value whatsoever, but it has a lot of value to me. But what we're talking about is 0 to T years when it would have monetary value. Therefore, the minimum value is 0 and the max is T. The car is going to depreciate from a maximum of D dollars down to $0. So the minimum value of Y is 0 and the max is D. So the intercepts are 0 on the X, D on the Y, T on the X, 0 on the Y, and it looks just like that. Very similar to the last equation, but this is a very general form of it. Okay, now we want to look at something very important because students who've taken Algebra 1 have heard a lot about slope, but if you don't contextualize slope, it means nothing. So let's take the same exact situation and now let's contextualize it. Right, we have 2 points. We got that point that was up here and that point that was there. And students know that the slope ratio is y2 minus y1 over x2 minus x1. So I'm going to take these 2 points and I'm going to do 0, 0 minus 27,000 and 12 minus 0. And I get this fraction here. Well, that fraction means something else when I simplify it. And really I should have written negative 2250 divided by 1, but we don't need that divided by 1. But what does it mean in the context of this problem? That's the slope of the line. It means that every year the car dropped $2,250 in price. So drop $2,250 per every 1 year. That's what slope is. It's a rate of change. So what we're going to do now is we're going to take a look at everything I've done here, and we are going to now take a look at what is known as a system of linear equations. It just means looking at linear equations that have more than one involved in them. There's an interesting little cartoon by Foxtrot. Let me give you a second to read it. I mean, basically what it's saying is the girl was able to figure out the problem perfectly in context, didn't realize that the contextualization of it was the same thing as the symbolization of it, and she kept saying, you didn't help me solve my problem. Well, that's true for many students. When we contextualize, we help them with the symbolic portion as well, and that's why contextualization is so important in mathematics. So we're going to look at this problem. Celine bought a new car for $33,600. She made a $4,000 down payment and pays $560 each month to pay off her loan. She knows from her research that the make and model of the car depreciates to zero over 10 years. Okay, I am going to do something that I call guided discovery with you, and you might want to jot some things down as we go through this. In other words, I'm doing a little hand-holding here, and I do this with my students in order to give them a technique of being able to solve this problem. So, because this is going to take a couple of screens, what I did was I left the problem statement on the top. We're going to write an expression for how much she spends, and we're going to write an expression for what the car is worth. So bear with me here. What was Celine's initial payment? Go back and take a look. Well, certainly Celine didn't pay $33,600 for the car. That's what the car cost. But she did make a payment. So this amount represents her first investment in the car when X is 0 months. Write that down. Put down what you think that answer is. How much does Celine pay per month? Well, that's easy. That's in there. Go find it. Write it down. You should have gotten her initial payment was $4,000. That's the down payment. And she pays $560 a month. All right. The reason I asked you to write this down is because now we're going to carry over to another slide. Okay. How could the ratio of the change in the total expense per month be expressed as a fraction? Okay, what's her only expense per month? Don't worry about maintenance or gas. We're just talking about loan expense here. $560 per month. What's happening? Every month she's throwing into the pot another $560. So to express that as a fraction, it's 560 divided by 1, or $560 per every 1 month that passes. This is going to represent the slope. There's our rate of change in expense in what she's put into that car. So we have enough information right now to actually write the expense equation. And that expense equation is going to use that slope and the initial amount of her investment. The expense equation is 560x, slope, plus the initial amount of $4,000. Jot that down someplace. Okay, now we got a problem here, and this is why I handhold the first time I do this with kids, because there's really two different periods of time in this problem. One is in years and one is in months, and we have to rectify that in order to be able to do a system, in order to be able to compare the two things that are going on. So the time X is in month rather than years, and since Celine's car will totally depreciate after 10 years, how many months is 10 years? Well, that's not so hard, all right? So it's 120. So from now on, we're going to forget about the 10 years, and we're only going to look at 120, because both equations have to be in the same amounts. That's going to represent the x-intercept of the depreciation equation. In other words, when 120 months have passed, your car's worth nothing. All right, what was the purchase price of Celine's car? $33,600. That's going to be the y-intercept of the depreciation equation. So I'm hoping that you can picture in your mind from what we saw in previous slides of a line that goes down with negative slope. It's going to start up at the point 0, 33,600, and end at the point of 120, 0. Now what we want to do is determine the monthly depreciation amount over the total number of months it's going to take for the car to depreciate. Okay, think about that. Monthly depreciation amount over the total number of months. Okay, well the car costs $33,600. There's 120 months. Divide $33,600 by 120, we get 280. An alarm should be going off in your head and in your student's head. Where did that number come from, that 280? We've seen that before. So what I'm going to do right now is I'm going to take these 2 points and I'm going to graph. The 280 is my slope. You've seen that number before because it's the depreciation amount. In the context of the problem, why is the slope negative? It's negative because the car is losing value by $280 per month. Write the depreciation function. Well, negative 280x plus the original price of the car. Now, students, it takes some time for them to get used to this problem. But once they see it, once they know how to set up an expense and how to set up a depreciation function, they fly with it. And this, I'm talking about students of all ability levels. Here's the graph. The red line here is my depreciation. It has negative slope. And the blue line here is my expense. It has positive slope. And what I love about this now is, ordinarily in an algebra class, you would have them plot two graphs, tell me where it intersects, we move on to another lesson. But in this class, this graph tells a story. And let's listen to the story. The graph intersects at the point 35.24 and 23,733 about. In the context of the problem, what is that point? Think about it. Here's what it is. After almost 3 years, a little more than 35 months, the value of the car, because of depreciation, is equal to how much money you've put into the car. And this is known as the break-even point. And then at this point, I say to the kids, what does that mean? What does that tell this particular car owner? And hopefully, they can now tell me this story. That when X is less than 35.24, if you notice on this graph, the red line is higher than the blue line, so your car is worth more than what you've put into it. When X is greater than 35.24, the blue line is higher than the red line, so your car, you put more money into the car than the car is actually worth. And what happens right in the middle? That's known as the break-even point, and you might want to consider getting rid of the car right then and there. That's interesting. I still have this 1998 Toyota Camry with 300,000 miles on it. When I would park it in the parking lot, right after I did this lesson, the kids would say to me, Scroy, if that's true that you're supposed to get rid of your car after 3 years, how come you still have that car out there? And the answer I gave every year, because that question came up every year, was, I'm a teacher. I can't afford to get rid of it. But in reality, we keep these things. But mathematically, that's when we should be getting rid of it. There are other forms, like I said, of depreciation: historical, exponential. In an exponential, this one would be decay, and it has a percentage in it. This is a growth function. This is for vintage cars that appreciate over time. And we can look at an example here. Here's a car. After 1 year of age, it's worth $24,230. 2 years, $22,355, etc. Here's what the scatter plot looks like. Here's, using my graphing calculator, what the exponential regression equation would look like. And here's what it looks like when you use the graphing calculator. All right, lastly, I promised you a little quick discussion of the bathtub curve. Now, think about depreciation and appreciation, and I think in your mind you should be able to get this easily. There's three main arenas here. The car is depreciating. Then, pretty much it levels off. Then it appreciates. What kind of car does that? A classic car. A classic car does that. Now, do I own a classic car? Absolutely not. Mine goes like that. But this is what we can look at. As a matter of fact, this graph also holds true for failure rates of new product. A new product comes out on the market, and immediately, these, after like a month, this is how many failures. And then let's think about an iPhone. Apple is continually sending us new updates. Well, but so there's fewer and fewer failures until finally they figure they have it all in hand here and things level off. But just because of wear and tear, and because most products are manufactured with something known as planned obsolescence, they're planned to die off after a certain period of time, the failure rate goes up. So here's another arena for using the bathtub curve. All right. Now we're going to look at driving safety. This is an interesting area because it allows me not only to be a math teacher, it allows me to be a parent, a police officer, all at the same time, because numbers talk. I have 3 daughters, and I could have told them, don't do this, don't do that when you're driving the car, but I know they did it anyway. But to be honest with you, when you look at the numbers are chilling when we start to figure things out. So a dashboard can give you a lot of information about the car's ability to go, but it gives you nothing about the car's ability to stop. Stopping means doing a little bit of mathematics. And what we're going to look at right now is what's known as the reaction time or the thinking time, and the reaction distance and the braking distance. Now, reaction time or thinking time is the time it takes you to realize your foot is on the gas, you've got to go from gas pedal to brake pedal, okay? That's the reaction time. And the reaction distance is how far your car goes in that time. Now, you may think, oh, I can do that really quickly. All right, let's take a look at a little math. And even though this is arithmetic, I love to do this with my students. There's 5,280 feet in a mile. A car is traveling at 55 miles per hour. It covers 55 miles in 1 hour. Make sense? All right, well, if it's traveling at 55 miles per hour, and if it covers 55 miles per 1 hour, well, there's 5,280 feet in a mile. That means in 1 hour, it covers 290,400 feet. Arithmetic, nothing more than that. Well, if there's 60 minutes in an hour, let me see if I can rewrite this now as an equivalent fraction of how many feet in a minute does the car go. Well, if there's 60 seconds in a minute, I'll divide that by 60, and I come up with a car traveling at 55 miles per hour covers 80.67 feet in 1 second. Students don't realize that. As a matter of fact, adults don't realize that, or they wouldn't tailgate like they do. I don't mean tailgating at a football game, tailgating on the road. If you think about these facts, you say to the kids, well, look, that 80.67 feet in 1 second is usual for the average reaction time. The average reaction time for a person is about 3/4 of a second to have foot go from gas pedal to brake pedal. But what happens if you're texting? What happens if you're drunk? What happens if you're playing with your iPhone or whatever, or you're distracted? That reaction time gets bigger, and therefore the distance your car goes in a second gets bigger. Very chilling facts. So what we found, though, is there's lots of formulas for figuring out the reaction time, but what we have found is that pretty much if your car is traveling at 55 miles an hour, in the time it takes you for an average person to go from gas pedal to brake pedal, it'll be about 55 feet your car will go. Now, in actuality, if you use the formula, which it's too complicated, we're not going to do that here, in actuality, it's more than that, 55. It's closer to 60. But you want something quick. Nobody's going to sit down with a pen and paper in a car and figure these things out when they're driving. But if you can have students remember, if you're going 50, it'll take about 50 feet to stop the car. So here's a check your understanding. You're traveling 65 miles an hour. It's going to take about 65 feet for the reaction time. But that's not all it takes to stop a car. Now we have to look at the braking distance. Now, braking distance is a function of a lot of things. If there's ice on the road, if there's gravel, if you have lousy tires. But we're going to look at the generalized formula for braking distance, and it's a quadratic. It's s squared over 20, where s represents how fast your car is going. Pretty simple, okay? So if the car is traveling at 48 miles per hour, s squared over 20 is 115.2 feet. So you have just braked, applied the brakes, and before you can stop, your car is going to go on average about 115.2 feet. Well, that's a lot. And I think kids don't get the sense of what that is. So sometimes you try to think, well, the average classroom is about 30 feet. Let's compare it. That's more than 3.5 classrooms, guys, for that car to stop. You can't stop on a dime. Think about a little kid running in front of your car chasing a ball. You can't stop on a dime, and that's why you don't speed. But here's the deal. It's not just the braking distance, and it's not just the reaction distance. Rachel is driving at 48 miles an hour on a one-lane highway. She sees an accident directly ahead of her about 200 feet away. Can she stop? I love to give questions like this. Well, the total stopping distance is the combination of reaction plus braking. And we said that the reaction distance is going to be s. Whatever your speed was, we'll make that feet. And then plus s squared over 20. So in this case, look, Rachel's total stopping distance is 48. She was going 48 miles per hour. That translates to, it'll take about 48 feet to react. And then 115.2 feet, total 163.2 feet. The accident's 200 feet away. Considering that this is just a simplification of it, it would probably be 170 feet, 172 feet in actuality. But these are things that speak volumes, and they speak volumes to kids. Let's try them. There's an accident ahead. Tricia is driving on the interstate at 64 miles per hour. There's an accident ahead about 250 feet from her car. Will she be able to stop in time? Let me give you a minute or two. Well, maybe a minute. Okay, the total stopping distance is equal to the reaction distance plus the braking distance. And we said the formula was s plus s squared over 20. It's a quadratic. All right, that's 64 plus 64 squared over 20, which is 268.8, which is really lowballing it. It's probably more like 270 something. So guess what? She's not going to be able to stop her car in time, and she may have to swerve to go into the median on the grassy part that you see in the picture there to avoid a collision. This is important stuff. So not only do we have information here about stopping and reacting, what happens if you are in an accident? And this is the part of the section that I really enjoy because, again, it hits home. At the scene of an accident, there's lots of data on the road, not just the pieces of a car, but there's data on the road. And that data are usually skid marks. And the analysis of skid marks by accident reconstructionists is very, very mathematical. As a matter of fact, it's a wonderful example of a square root function. And you don't find a lot of these that kids could understand. Here's a square root function. S equals the square root of 30 times D times F times N. D is the skid distance. And what accident reconstructionists do is they measure the length of the skid. If there are all 4 skid marks, they take the average of 4. If there's only 3, they take the average of 3. If there's 2, etc. If there's 1, they use that length. F is the drag factor. It depends upon what the road is made of, and that's a number that you see on that chart. So it's just an index. And N is your braking efficiency. How efficient are your brakes? Are they 100% effective, 80% effective? A mechanic could tell you that. So let's do an example. A car is traveling on an asphalt road with a drag factor of 0.78. The speed limit on this portion of the road is 35 miles an hour. The driver just had his car in the shop and his mechanic informed him that the brakes were operating at 100% efficiency. The driver must make an emergency stop when he sees an obstruction in the road ahead of him. His car leaves 4 distinct skid marks, each 80 feet in length. What is the minimum skid speed this car was traveling when it entered the skid? All right, so we're going to use the formula here. S equals the square root of 30 dfn. There are the substitutions that we put in the formula. We simplify the square root of 1872. The car was traveling at about 43 miles per hour. Guess what? You can't fight this data. You know, people will often say, but I was going below the speed limit. All they have to do is measure the skid marks, get the right numbers for the indices, and no, you weren't. So in this particular case, this driver was not going at 35 miles per hour, so would get a ticket for causing or inciting this accident. Now, this formula is only used when the skid marks are straight. When skid marks have curves in them, they're not known as skid marks anymore. They're known as yaw marks. And there's a different formula, and there's some geometry that needs to be used here, because in the formula, we need to find the radius of that skid mark. Now, the skid mark is an arc, and what accident reconstructionists do, and you've probably seen them on the road, is they take what's known as a trundle wheel, which is a rolling ruler, and they draw a line from two parts of the arc, which is known as a chord. Then they drop a perpendicular. Oh my goodness, we're using the word perpendicular in real life. And they're able to figure out the radius of the circle. And it was interesting, I included this little piece from a newspaper clipping because after I had done this talk, a student, there was a terrible accident in 2012 in the Bronx, and a lot of people were killed on a parkway. And the local newspaper said, a study of the yaw marks on the parkway, and my student brought this paper in and said, you didn't make that up? And I was kind of shocked that they thought I would just make something up for the sake of contextualizing. I said, no, it's real. Accident reconstructionists actually do that. So sometimes I think students think that when we're doing real world, and I use air quotes around that problems, sometimes they really are phony, and they can tell the phony problems. These are not phony. As a matter of fact, there's so much more in the algebra of the automobile. There's the algebra of auto loans. It's a great topic that you can look at. There's the algebra of auto leasing and auto renting. There's the algebra of automobile engineering and manufacturing. There's the algebra of fuel economy. That has its own algebraic analysis that can be done. And then there's the algebra of marketing and sales. There is a lot of mathematics inherent in the automobile. And it's a perfect way to motivate students. Now, you can do all or some or part, whatever of these things, but I have, from my many, many years of experience, have found that students latch onto them, they use these as an anchor, and they remember. Anybody have any questions?
We don't have any questions right now. We can give everyone a couple minutes if they want to submit something. All right, we have a hand raised from Linda Dachdow. I'm going to unmute you so you can ask your question.
Hello.
Hi.
Where did you, were you in your PowerPoint getting materials from a particular textbook, or where do you find your sources of the differing examples? They were very interesting, I found.
Well, the sources, when we originally put this program together, the sources we found on the internet, and by over years and years of teaching this sort of stuff, we found them in resources. But, I mean, and I'm not plugging it, but all of this stuff is in that book that I showed you at the beginning because we've written this course with that.
Oh, thank you. Okay.
Sure. Well, then let me thank you, and I hope that you're able to take some things away from this session. And I encourage you to join us in April for the next two sessions, which I think you'll enjoy. One has to do with projects, and the other has to do with banking and compound interest. So have a good day.
Thank you for joining us for today's webinar. As a reminder, this will be available for viewing at nyctecenter.org within 72 hours.